So I did want to point out, because I did get some questions last night about where the actual class videos show up. So there's two places you can go to. It will be on my website, but it will also be on the YouTube channel itself. So what you can do is either go to my website every week. It will probably be posted anywhere between Friday and Sunday after the class occurs. But if you do subscribe to the YouTube channel, you can set up notifications for it to basically notify you through email or whatever, in order to look at that YouTube video when it gets posted by me. So two options there. The links are available. To get this slide deck, just to point out, you should go to Machine Learning Introduction, the bit.ly link up here. So all right. So today we're going to be really diving into the machine learning and the different types of models and how you prepare your data for that machine learning model. So to go over a little bit about what machine learning is, I'm going to cover this pretty at a glance, because you probably, if you're in a machine learning class, you probably know at least what it does. But machine learning, when I've done a few presentations for third graders about like coding and machine learning. What I usually tell them is it's predicting the future before it happens. But in reality, it is actually taking historical data, using that historical data in order to make like predictions based on what has happened before, to inform future decisions before they happen. So we can test before we actually put something into production, the accuracy and some other metrics as well, to try to get an idea of how good our model is. And then it will give us some of those insights before we actually go into the production of the machine learning model. So there are different types of machine learning algorithms that we use. For the most part, there's 4 buckets. Things are getting added on more and more that sit outside of these buckets, but the main ones are first, classification. So a classification model basically predicts a categorical variable using known class labels from historical data. So it takes what has happened in the past. The example I'm giving here is predicting whether a substance abuse treatment admission is the first or a readmission. This is going to be our example from class to go through. So we're predicting whether if a new individual comes into a substance abuse clinic, whether it's a readmission or it's their first time there. So we take that historical data, try to build a model to predict known class values in that historical data. Then we apply it to unseen data. And it can be a yes/no a prediction, or it can actually be something called multi-class prediction, where you predict something with more than one level. So high, medium, and low would be an example of a multi-class predictions, where we have more than just a binary or 2-group prediction. Regression, don't get this confused with like linear and logistic regression. This or with linear regression itself. So this is like a bucket term, and linear regression would sit below this larger bucket. So regression is trying to predict a numeric variable, so something that is numbers and goes on a scale, versus a category, which is like a yes/no. An example of this is a project that projects that and you do in agriculture, which in sometimes predicting crop yield is something that they try to do to enhance business understanding when they're making decisions about, say, which crops to move on in their testing pipeline. So that is what a regression is. So the difference between that and classification is the prediction of the continuous variable. Unsupervised learning is a bit different. So up here, we call this supervised learning. So we're taking known class labels and actually predicting something. Unsupervised learning is actually, we don't have known class variables. So we're looking at patterns in existing data to make judgments and to find patterns in data that doesn't have labels. So a really good example is clustering stores for retail, where you take stores and you could take sales data, you could take demographics of the neighborhood it's in, say the number of people that are actually making transactions. They even looked at parking in one example that I did, because it affected whether people, say, came into the store or did a delivery option. So it then would cluster like stores that have similar characteristics into different groups, so that you would be able to maybe see which clusters would be best for business development. So adding more stores versus, say, a low revenue store where you wouldn't want to actually go add new stores. Reinforcement learning is something that's completely different from all of these up here. So again, we don't have any known class labels, but we set up an experiment basically, and we tell the the model to basically go through a process where it either fails or succeeds. If it succeeds, it gives it a reward. If it fails, it gives it a penalty. So then it takes that penalty and reward information to the next run, improves the model a little bit, and runs it again. So we're taking those, the feedback from the model and those rewards and those penalties to improve the model. And then we end up having like something more closer to supervised learning. But the idea is you would run this over and over and over again, see where it fails and succeeds. Instead of the example here, a more simple one was one of the first machine learning cases that they used that was known by the public, where actually they taught a machine how to play chess. And then the machine actually was able to beat the best chess player in the world. And ever since it was created, it has beat the human chess player every single year. No one has ever been able to beat the machine in that chess after it created a reinforcement learning model. So that's the difference between the different types of machine learning models. For the people that came on, we are recording this class, so just FYI, it will be posted and I'll show the links before class is over after class. So that's a little bit about the types of machine learning models. So classification or regression. So in a lot of cases, we turn classification or regression models into actual classification models. So I'm going to mute all participants since nobody's talking. So in one example is something that I did. I was actually doing a project where I was predicting revenue from different business ventures. So what I actually did, instead of actually predicting that revenue number itself, I actually turned it into a classification model. I talked to the business owners and I said, okay, what revenue amount would be a cutoff for where the it would be a meaningful or a high value business venture versus a low value business venture. And I actually predicted that classification. When you would want to do this is in a couple cases. If you have really messy data, which was definitely the case in this particular instance, actually taking that classification might be more predictable than actually predicting the revenue number itself. Another case where this is often a better strategy to turn a regression model into a classification model is if you have a lot of outliers in your data, and the outliers aren't necessarily as meaningful, and you don't want to predict those outliers. Those outliers can basically make a regression problem harder to predict. So in a lot of cases, taking it and turning it into a classification model is the best strategy to get the best bang for your buck. Are there any questions about the difference between a classification and a regression model? So classification, for people who join late, is predicting a class, like a yes/no variable, which is whereas regression is actually predicting a continuous variable. Are there any questions? I have the chat open, so feel free to chat or unmute if you'd like. All right, no questions, but feel free to put anything into the chat and I will definitely see it and come back to it if you'd like. So a couple examples from the field so you guys can picture what this actually would look like in a business context. So one of the more successful models I've done in my career was actually an agricultural model. It looks like my old coworker is on here, so he knows and is intimately aware with what I did here. So we actually, I was in the testing process at Bayer before it got made new products into commercial products that were for sale. But in order to do that, you had to actually produce enough seed to support that entire testing process. So my model actually predicted whether it would reach enough seed. It predicted a seed return that would then go into the testing process. And there was a cutoff, like if it was below a certain level, they had to scrap the whole product and start again next year from scratch. But if they predicted it and hit that seed target, it would make it so they wouldn't have to start over. So we were able to actually decrease costs in one place without increasing failure. And in the other place, we were able to decrease failure by 70% with my model. So that's an example from the field. Another one was actually for a technology company, predicting high and low revenue for different business opportunities. So they would be able to actually find those high value business opportunities quickly and before they actually had to test whether it would be high revenue or low revenue. Another one that I've worked on in the past is actually extracting text from images. So if you have different documents, you can run a deep learning model that will take that text and predict what that text is. So people don't have to go in and transcribe things. And the example that we're going to use in this class is predicting individuals who are at high risk of relapse from a substance abuse disorder. So individuals who would be checking into a substance abuse clinic, they could then find out if they're high or low risk for relapse, and then they could tailor treatment strategies based on those characteristics. So a little bit more about the example I'll be using today for the machine learning example. So the data includes every admission to a substance abuse treatment center that is publicly funded by the government. So if a substance abuse treatment center is receiving Medicaid or Medicare funds or any public funding, it will show up in this data set, meaning it's very large. I did make some concessions and subsetted the data to a smaller number of observations and made that available for you guys to use so it wouldn't take as long to run the code. It is saved under data in my OneDrive as it has small in the name, and I'll show you where to plug that in so you don't have to go through the whole data setup process. What we would be trying to predict is all right, there's a question. Sorry, was extracting text from images a reinforcement learning approach? Actually, no. So an example of how that would work, and I want to go real quick, I'll go back to this slide. So there's a service, for instance, in Azure that does this, and there's a model working on the back end that Azure created and Microsoft created. So an individual would go in and for say 100 documents, go in and say, okay, here's the label. So first name is located here on the document. And it would say, in my case, say Kelsey was the first name. They would go in, tell the ground truth, so what the values actually are in all the different forms. And then you would do that for every label. So last name, you would put Mnet in my case. And you would do that for about 100, 200 documents, actually transcribing them directly. And then the idea is after that, using every single image, the model would compare, it would predict something and then compare its prediction to the truth that you gave it. And then every time it would actually improve that model and improve it over and over again in order to be able to predict that text extraction on new data. So using that uh, the labeled data in order for that. So that's a little bit, it's definitely supervised learning. So it's a bit different from this because it's called computer vision. So that's actually something I should add into here. Computer vision isn't really a classification or a regression model. So yes, the same, you'll find that across all the cloud platforms, the services are very similar. They're just called something different. Azure Forms Recognizer service was actually what I was describing there. All right, and we can go back. Thanks for interrupting. I love questions. So we would be trying in our case today, coming back to the example that I'll be showing, we would be trying to predict which admissions are first time admissions and which are repeat admissions. Ideally, you would want to use time series data and follow the same individuals over time, but this is just something that isn't available. So this is the best we can do in this circumstance. But the goal would be to predict which individuals are at high risk for relapse upon admission, or so that they would be able to tailor treatment strategies to help them not relapse. Right. So the next thing, I want to take a little bit of a detour. So if you were at my first couple of classes, I'm basically repeating a lot of the material from what I did first. But in this time, I want to go into a little more detail and not go at a high level. I'm going to go over the same stuff, but I want to give more background information, because one thing that I've noticed about machine learning, and unfortunately, it takes a while to understand this stuff, but hopefully I'm giving you enough of a glance of what the end looks like for you to be patient to go through that. But understanding what happens on the back end actually helps you make decisions as a data scientist that are essential, so that you make the right call. I want to go back to original. If you've had statistics 101 in college or high school, you'll have seen this before. But it's important for the next thing I'm going to talk about in the pre-processing step. So a detour, I want to talk about the normal distribution and z-scores. So the normal distribution looks like a bell curve. If you have data on this bell curve, you will see basically the middle is where the mean's going to sit, and you look basically how far away your different values are from that mean. And I think I got a chat message, but it was not from here. So I'm going to just make sure nobody's lost. Okay. I don't know what happened there. So the normal distribution looks at that, like what are high values versus our low values, how close they are to the mean. It is usually symmetrical, meaning that it does have this bell curve shape, and the same amount is on this side as it is on this side. So if it is symmetrical, Your mean, your median, and your mode are going to sit here in that middle. If it's skewed to one side, so you have more high values than low values on one side, it won't have its mean and median in the middle. So that's also good to know because different models handle outliers better than others. So you kind of need to know that distribution and if there's a lot of outliers in your data before you make a decision about which model to use. So normal distributions can also differ in their shape. So all of these shown here are normal distributions. These have the data values that are much closer together. Whereas you're seeing this one, they're a lot more spread out, but they still have the same shape or the distribution. So in this case, the standard deviation, which measures the spread of your data, is going to be more spread out or a lot higher. You can think of it also as more dense or less dense. So a little bit more about this. So as I said, the mean and the mean always sits in the middle. So regardless of what your shape is, the mean is always going to sit here. If it's symmetrical, your median and your mode are going to be close to this amount. But for a normal distribution, the mean would sit here and you would go one standard deviation to each side in order to see it, to look at your data distribution. If you need a refresher on what a standard deviation is, please feel free to go back to my statistics in R class sitting on my website. It goes into this in detail, but it's based on the mean, each individual value, and the number of values in your data set. So basically, if it's a normal distribution, if you go one standard deviation to the front and one standard deviation to the back, which sit here, about 68% of your data is going to sit here. So the vast majority of your data is going to be in the middle. And as you go, say, 2 standard deviations to the left and 2 standard deviations to the right, that's going to encompass about 95% of your data. And so on and so forth. If you go out 3, it's going to get 99% of your data. So why does this matter? This comes back to something called data pre-processing. I'm gonna hit it in the next slide, and actually I think it would make sense to do that one next. So the data pre-processing step, it was the slide after. Basically, machine learning models in most cases are based on distance. There are some exceptions, and those tend to be the tree-based models. Those would be decision trees, random forest, and gradient boosted trees. We'll cover them later. But for the vast majority of models, they're based on distance or a gradient. So if you have data that has a much larger spread, so example of this would be median household income. So if you're looking at median household income, it's going to range from, like, say, $10,000 on the very low end up to maybe millions of dollars. So it's going to have a really large range. Whereas if you're also using in your model, say, the percentage of white individuals in a county, for instance, it's going to go from 0 to 100. The problem with using those data as is, if you're measuring distance and you haven't pre-processed your data, it's going to weight those values with the larger range as being most important and tailor your model to that effect. But even though it's not actually, it might not be the most important variable. So this would be something that would be called biased. So we want to get the ground truth and what is actually important. So the way that you handle this is actually putting all of your features that you're using to predict your target variable. So the final prediction, the features are what you use to make that prediction. You want to put them on the same scale. There's a couple ways to do this. The one that I find I use most often is actually called normalization. And that takes each individual value in your data set, subtracts the mean, and then divides that by the maximum minus the minimum. What this does, and you can see here, it makes every continuous variable, so your numeric variables, and it puts it between 0 and 1. So no matter what your data looks like, it's going to sit between 0 and 1. The standardization comes back to the normal distribution we just talked about. So what this allows you to do is to basically put your data and scale it to a normal distribution. That way each individual continuous variable is still on the same scale. So in this case, you would take every value in your data set, subtract the mean of the entire feature, and divide by the standard deviation, which would be related to the spread of your data. Why would you want to use one over the other? So normalization, no matter how big the outliers are going to put them on the same scale. So it sounds like somebody's trying to get on the wrong link for this class. I probably don't have time to go in and add it on the chat. So that takes that and puts it on the same exact scale every time. So the standardization method is best when you have meaningful outliers. So you have those revenue numbers and that those outliers actually mean something. So it makes it so that those outliers actually are bigger than your middle, I guess, or the bulk of your data. They're still within a smaller range, the same range, but those outliers will have more meaning. So that's something to keep in mind. In reality, we would usually try both for our machine learning models and compare the accuracy. Right. Okay. Now coming back to categorical variables, this same concept fits here too. So we want to have something similar to the same range. There's a couple ways to do that. So if you have unordered variables, that is the method you want to use if basically one category is not higher than another. So if one category is higher than the other, you want to take a different approach. So example of this is shown here, and this is from our actual data that we're working with today. And that is an example of having mental illness versus not having mental illness. One is not inherently bigger than the other. In this case, we want to use something called dummy coding. The dummy coding takes each category here, which is 2 in this case, and it makes 2 features, one for has mental illness and one for does not have mental illness. So that has mental illness will have a 0 when someone does not have mental illness, and a 1 if they do have mental illness. It will also create a does not have mental illness, where we have a 1 if someone does not have mental illness and a 0 if they do. In reality, especially for dummy variables, you always would want to drop one of these columns. In general, using features in a model that are highly correlated with one another actually makes the models less accurate. So you can see here that these are perfectly correlated, meaning that they show the same information just in a different format. So you'll always want to pick one to drop from your model. In this case, you could do does not have mental illness. Your model is going to have the same incoming information. You do that for every categorical variable. So ordered is a bit different. The example I have here is age at the first use. So in this case, 12 to 14 years is clearly lower than 30 years or older. So this value is always going to be higher than this value. you still want to keep a numeric encoding. So you want to keep your categories as numbers. But in this case, you would want to do a 1, 2, 3, 4, 5, 6. So that is an example of how you would do an ordered category. So now you would have something that is all on a similar scale to one another. That would be able to go into a model that's based on distance. Are there any questions about this before I move on? All right. So this is one of the first things that you want to do. I'm going to actually come in and show you this in code and how this would work. So one thing that I would say in this data here, it may, because it is easier to use a smaller data set when you're learning. You may want to actually come in and read in the data here. That data is sitting in storage under that bit.ly link, under the data folder. This will allow you to be able to run the code without going through the entire process of with the 2 million or 4 million row data set. So I recommend reading it in here. I actually should move this up and before the dummy coding. I'll do that after the class, so you'll be able to see this in action and run it if you want. So I should have subset it up here, and I'll read in the data again after class. So I want to show what the get dummies looks like. So in our original data set, before we get and create those dummy variables, this is what our feature set looks like. So we have, in this case, an alcohol flag. So did they have alcohol in their system when they came in for treatment? We have an education variable here. So are they well educated? That could be correlated with a relapse rate. An example here is the frequency of use of the individual drugs that were in their system upon admission. So this would be the highest frequency of any of the drugs that were in their system. So we, in any category that is not a 0-1 variable, which I already took care of up here, you'll notice that all the 0-1s I already categorized as 0 or 1 when I recoded them. So we're not going to include that in our get dummy variables. This just makes it so we don't have to redo work and get rid of one of the features. So in this case, anything that is a category that has more than one level, we're going to put in this get dummies. So when we run that, and if I ran this, I've already run it, so I'm not going to rerun it. I wanted to be so you guys wouldn't have to wait for the answer. So our columns will look something like this. Oh, that's why. So my keyboard is actually not functioning correctly. I am going to open my laptop in order to be able to type in and code on the fly. So I will move that over here. Apologize for zoom in. I will zoom in, definitely. Okay, do that before. I'm not sure how the best way would be to do that on a Mac. So I'm just going to go into the view and do that anyway through here. Be the easiest way. All right. Hopefully that's big enough for you to see. It's much bigger. I don't think I can make it much bigger to be able to see everything on one screen. So what I wanted to do down here is actually take that TEDS 2018 data and look at the columns inside of it. So now we'll have a little bit of a different thing after getting the dummies. So in this case, we have race. It's P source is basically how they're taking the drug. Division is related to region. So I'm going to actually take one of these, and hopefully I don't get confused. When I use, in general, Spark and Python at the same time, sometimes I get a little bit mixed up between the two. Dot value counts. Let's run that as well, so you can see the relationship between the two. Oh, because I deleted it below. That's why. Okay, so I'm going to rerun this real quick. Shouldn't take too long, so that I can show you the process here. So it's going to take that TEDS clean, rerun that now, print the columns. Not sure where that went. Okay, so it's going to get the dummies here, and then I will show you. Let's look at TEDS clean. Group by race value counts. So, not sure what's going on there. I did want to show you what the different values for race looked like. We can do that another way here by doing display, where I can show you the top levels of the data. Actually print this. And that'll take a minute to run. So here we go. So one of these examples, P source, what I just talked about, is whether a individual is referred, and how they are referred to substance abuse treatment. So that's an example of one that we're putting through our variable. So now, if we go down and look at that P source category, we have each individual category. So alcohol, drug care professional, community referral, all of those now have their own column. So they are going to be a 0-1 column instead of that, having the different ones, so having that in different categories. So I'm going to rerun real quickly the thing that subsets our data, and that will make it so that things run a lot quicker. So this is subsetting our millions of rows randomly into 200,000, so things run more quickly. So now I can take that TEDS 2018, and we can look at what this looks like instead. So now it's actually showing different examples here. So this will actually be good as well. So we also have in this data set marital status. So now all the different marital status categories have their own column. So married, never married, separated, and all have their own category. Now, we are going to go back to the slides very quickly and go over the next part. So handling missing values, toggling back very quickly, you would have seen above here that there is quite a bit of missing data, and this is an example of it. So whether there is oral drug use or not, it's not showing up in our data, it's missing. So some of the dependencies for this are missing. We want to deal with that by imputing the missing values. If you don't impute the missing values themselves, they will actually, every row that is missing, the machine learning algorithm will take that and it will actually remove it from your data set, which is not something that you would want to do. So we don't want to lose that information. So we're going to basically take our best guess on what the missing values would be. So in this case, the best way usually done is called simple imputation. So taking the most frequent value or the mean or the median based on what our data looks like and actually replacing that in for each individual feature. The more complex methods research has shown don't actually add much value. So we want to use the most simple method possible because doing the more intense algorithms actually, they're very computationally expensive. So what they find is that the complex machine learning model actually makes up and takes that information and you end up getting the same accuracy from that smart machine learning model either way. So there are a couple different ways to deal with missing data. So an example that you could use is actually imputing it. Another which would be useful in some cases, I don't normally do it, is to make missing its own category. So instead of making it or guessing, you could say data is missing. A case that you would want to do that is when things aren't missing at random. So that missing value actually means something. It has meaning and would help your model predict better. So coming back in here, we are using something called a simple imputer here. Since all of our data is categorical, all of our features, we're going to pick the strategy equals most frequent. So that it's not going to, we don't want it to find a mean of the category values. That would make it so our data was incorrect. So we're going to take that, get the mode or the most frequent value, and we're actually going to impute that by getting and filling in that most frequent value. And then all of our missing data will then be gone. Those missing values will be filled in by a value. We've talked a lot about changing everything to a numeric variable, even our categories. The reason for that is that, again, we're finding distance in a lot of cases. And you need, in order to find distance, you can't find distance between two categories. So the next thing that you usually want to do here is change everything to a NumPy array. That's just how the models actually expect the data to come in, not through a pandas data frame, but that NumPy array. And that allows it to occur a lot faster and to make sure everything's numeric. Are there any questions about imputation before I move on? All right. So I just covered this in the code. The NumPy arrays need to be, and everything needs to be in numeric form. The next couple of things that you need to take care of. So the response variable has to be in a separate NumPy array than your input features. That's just something in every language that you see, for the most part, you'll see that you have to do this. R might be an exception. I'm not sure about that. So you'll have what you're trying to predict, your target or response variable in one NumPy array, and the other or your features in another NumPy array. So you're seeing that I do that here. So the features are in here, and I actually subset it up here. No prior is our target. I subsetted it for the pandas inside the pandas data frame because NumPy arrays don't have column names. So it's easier to do it up here. And now I'm able to actually convert to two NumPy arrays and have one, the response variable in one, and the target variable in the other. And we've already talked about this as well. Any missing values need to be either removed or imputed or handled in some way. So this part is extremely important. It's no matter what you do in machine learning, you're usually having to do some type of validation. It looks like this that I'm about to show. For supervised models, this is how you would do it. So I've talked about this a little bit already, but we want to take our training or historical data and make a model to predict new data. In order to do this, we need to have something to test it with. So in a lot of cases, in the case I'm going to show, multiple ways to do that. But the one I'm going to use as an example is we take our training data, we put say 60 or 70% of our data into a training data set. We have say 20% in a validation data set, which is what we use to actually compare our different models side by side and see how the accuracy or the other validation metrics compare. And then we have something called a holdout data set, and I'll cover that in a minute. But what we tend to do in modeling is we change something called hyperparameters in our models. So it's tweaking and changing the model in a small way. An example in linear logistic regression is called a regularization. So it basically takes coefficients, or you can think of them sort of like our weights in our model, and it makes it so that the smaller coefficients actually go closer to zero. So our weights and there are go closer to zero, and effectively our zero features are completely removed from the model. So those that aren't as important. That's an example. And in reality, you usually test multiple hyperparameters. And in different models, there's sometimes like a dozen hyperparameters to choose from. You test each model side by side, compare the accuracy metrics, and then choose your best model. You do that by actually validating it with another set of your data other than the training data. And the holdout data set, you always want to do this, even if no matter what technique you use, if you can. It's best to keep a data set, it's usually about 10%, as completely unseen data. So since you are using your validation data throughout your training process over and over again, that can create a bias in your accuracy. So they might look better than your accuracy really is. So keeping that unseen data that hasn't been seen in training gives you a really accurate and unbiased prediction of how accurate your model actually is in reality. So one of the techniques, and this is the technique that I'm using in our code, is called the shuffle split. You often see it as like a train test or shuffle split. This takes it and puts the bulk of the data in the training data. That's what's shown down here in this figure. So your training data sits in this gray area. After your model is trained, you compare that to your validation data set to get an estimation of what the accuracy is for each model that you try. Then you try many, many models and compare the accuracy. Again, our holdout is sitting there. So for a final accuracy test, after you've already chosen your model, it doesn't serve a purpose. It defeats the purpose of using a holdout data set if it's not moved and used outside and never seen before. We want to take our final model and actually use the holdout data to get a final accuracy estimation. So the second method that is pretty common is a k-fold cross-validation. It looks like something like this. We still have our holdout data, so a 10%, or in this case 20%, that is totally unseen in training. So that works the same way. But k-fold cross-validation actually trains for each model that you try, trains 5 different models, or whatever. You can actually do 10 different models, 3 different models, whatever you choose. That is called K. The ideal usually is around 10. So it takes, say, 5 sections of your data, predicts or you validate it on the final like fifth section. And then you move on and use a different 4 sections for your training and compare it to a different 10% section of our data, and so on and so forth in each individual one. So each row in your data is used in training at one time, exactly one time. We're randomly choosing in all of these cases without replacement. So we're not putting that back into the bucket. Then you can, in general, you take those accuracy metrics from each run, and then you find the mean of them overall in order to get one accuracy number to compare side by side with your other models. One other thing that you have to decide with k-fold cross-validation is how to use, which k to use. So how many models do you want to train? Shown here is k equals 5. So we have 5 different sections and we're training 5 different models. The ideal research has shown is about 10. You have to make a trade-off here because machine learning models take a long time to train for the most part. So when you're doing something like this, it's very computationally heavy. It might take a lot longer to run 5 files than 3 or 10 versus 5. So based on your model size, you have to make a judgment of how long you want to wait if you decide to use k-fold cross-validation. A smaller k is going to be like take less time to run because it's fewer models versus a 10k, for instance. And another thing that you want to keep in mind when you're doing validation of your models is stratification. So stratification makes it so it's randomly sampling your data, but it is keeping the distribution of your target variable the same when it randomly chooses the different sections of your model for training and validation. So when you want to use stratification is actually for unbalanced data, for when one of your target sections has a lot less rows in it than your other target variable. So say you have 60% are a 0 and 40% are a 1, or it can be even more extreme than that. Because randomly choosing has an error involved in it, and it will look different every time. Having that stratification might ensure that you have enough values in that in your target variable that you're using for training. So the more unbalanced your data, the more you're going to want to definitely use stratification. I want to go over a couple more things. Hopefully we'll have time. Actually, I think I'm going to stop and let you guys ask questions. One, I will go over a couple other methods that you use for small sample sizes. And then I'll also go over next time the pros and cons of the different validation methods themselves. So I'm going to stop for questions since we have 4 minutes left. I don't want to get too far into this. Understanding the k-fold cross-validation and the train test split is something that you really need to understand. So if you have any questions, please feel free to put them in the chat. All right. I will show one more thing, just so you know where to go on my website. Feel free to still put questions in the chat. So kelseymnet.com. If you miss a class and you want to see what's going on, for the machine learning, you'd want to go to tutorials and videos, machine learning, and all code will be located here. And you'll be able to see the videos and class materials. This was the last class. It had all of our links that we use, one of our videos from one of our sections, and it has the slides here. You can also download the entire slide deck by clicking this. And that'll allow you to go back and actually go and see those videos if you miss. Another thing that may be useful on my last slide here. Okay, I'm going to answer the question because I think that's the most important. Did you, after a train shuffle split, usually check about the mean, median, deviation as the same on the complete data set? That's actually a good point, and that's something that you would probably want to do because you're going to run into more problems when you have data that's more spread out. So we're not using a continuous variable in our case, but it would be something to definitely look at. And then if you needed to, you could probably take measures if your training didn't look like your validation. So in that case, your k-fold cross-validation is going to be the better option, because you'll be training multiple models on different subsets of the data, and you'll be able to find the mean of those. And if it varies a lot, the more K you use, the better it's going to be. And that would be a good way to deal with that, because each train and test data set would have a different mean, median, and mode. And overall, since you're testing multiple, it would probably even out to the real accuracy number. So that's a case where you would definitely want to use k-fold cross-validation. All right. One more quick thing so you can look at it after class. I'll also put some learning resources here where you can go and learn more about machine learning. I've read these cover to cover multiple times, and they're really helpful. I also have open data sources sitting here. And if you want to actually go in and try to model yourself, these are a lot of freely available data sources. Feel free to go Google the names of these and you'll be able to find them. Based on what you're interested in, this could be pretty helpful. In my R, statistics and R class, I also have a lot of clean data sitting in there. So that's on my website. Please feel free to go in and look at that. All right, thanks so much for attending today. I really appreciate your time, and hopefully this was helpful for everybody. I'm gonna sign off.